Good morning, dear students. This morning, we will discuss about coefficient of variation, standard error, and confidence interval. So, last time, we discussed the measures of central tendency, measures of variability, and measures of position, and we ended with computing for decile, quartile, percentiles. This morning, we shall start with coefficient of variation. So this is another measure of dispersion. But the previous measures that we have discussed, like your standard deviation, variance, mean absolute deviation, range, interquartile deviation, interquartile range, are absolute measures of dispersion. But the coefficient of variation is a relative measure of dispersion or of variation. Now, what is coefficient of variation? Now, coefficient of variation is simply the ratio of the standard deviation to the mean, sample mean. Okay, so it's the ratio of the standard deviation S to the mean, sometimes expressed in decimal or percentage. Okay, so after multiplying by 100%, okay, the coefficient of variation is expressed in percentage. Now take note that S over X, okay, S and X will have the same unit. So for instance, if the numerator's unit is kilogram and denominator is kilogram, that will cancel out, which means that your coefficient of variation is without unit. Okay, so usually it's expressed in percentage. So CV, we can abbreviate it as CV. CV is equal to S, which is the standard deviation, and X bar, the mean, times 100%. Okay, so S over X bar times 100%. So just the same as the previous. 100% times standard deviation over X bar. Now, how important is the coefficient of variation? What is the significance of the coefficient of variation? How different is it from your variance and from your standard deviation? Now, to illustrate the importance of the coefficient of variation, let's consider two data sets. Okay, we have here two sets of data. Set A consisting of the observations 2, 4, 6, and set B which includes or which consists of the observations 54, 56, and 58. Okay, so set A and set B. Now, we calculate the mean, the standard deviation, and coefficient of variation of the two sets of data, and we shall try to compare. Okay, looking at the letter A, data set A, 2, 4, 6, obviously the mean is 4. Yes, the mean is 4. Now, you can use, by the way, your Excel functions to find, okay, or to calculate for the measures of central tendency, measures of variation, and even your position, quartiles. You can use Excel. Okay, let me just, okay, so for the dataset A, let's say dataset A has the values 2, 4, 6. Now, just to show you how to use the Excel function in solving for the mean and the standard deviation, variance. Okay, set B, let's label. Okay, so to distinguish between set A and set B. So your dataset A consists of the values 2, 4, and 6. Sorry, 2, 4, and 6. And dataset B has the values 54, 56, and 58. Okay. So, equal sign and type average. Oh, there you have it. Average, and then you just highlight dataset A and close it in again a pair of parentheses, and that gives the mean. So, let's color it. Okay. Equals. What about mean of dataset B? Equal sign and then type in average. Okay, there you have the average. Okay, function and highlight dataset B. Okay, so this is the mean of dataset B. How about the standard deviation? Because if you going back to the problem, it also requires, okay, the problem also requires the standard deviation and then later the coefficient of variation. Because we cannot solve for coefficient of variation unless we know the standard deviation. Okay, now going back, so SD, let's denote it as SD for standard deviation, or S equals, okay, so type using again Excel function standard deviation of a sample. There, standard deviation of a sample, and then highlight. Okay, so the standard deviation of dataset A is 2. What about dataset B? Okay, so standard deviation again, equal sign there it is, standard deviation for a sample. Okay, highlight the scores or the observations. Okay, so the standard deviation is also 2. So looking at the comparing and contrasting between, okay, the two, let's compare and contrast between the two. Okay, so the mean of dataset A is 4 while the mean of dataset B is 56. Now notice that they have the same standard deviations. Okay, the standard deviations are the same. But does it really tell about the degree of spread of the values in dataset? Because if we try to look or compare between sets A and B, you notice that the values in set B, take note, the values in set B, let's compare 2 and 54. This value is 52 units more than 2, yes? 56 also is 52 units more than 4. 58 is 52 units, okay, more than 6. So, the values in set B are simply obtained by adding 52 to the values in set A, okay? But you might say the variability should be the same because of that, because these values are simply obtained by adding 52 to each value in set B. But that's not really the story. If we look closely, let's look closely, okay? Look closely at data set A. Take note that one value, let me highlight, 6. Okay, 6 is triple or thrice of the first value, which is 2, yes? Okay, so in terms of the scale of this data, its variability, set A, I'm referring to set A, is quite a lot. Okay? Okay, compare it to set B. One value in set A, which is 6, is thrice the first. But we cannot say the same thing to set B. Okay, so that means that the variability of set A is more than the variability of set B. However, the standard deviations are equal, which means that we have to look into another measure of variation that takes into account or into consideration the scale of the data set. And that's where your coefficient of variation comes in. Okay, so that's how significant the coefficient of variation. So let's continue by computing for the coefficient of variation. Let's find out which between the two sets of data has the greater, okay, variability or greater coefficient of variation. So CV. Okay, what is CV once again? Going back to our formula, CV is standard deviation over mean times 100%. Okay, so equals standard deviation 2 divided by the mean times, okay, times 100%. Okay? So, the coefficient of variation of the dataset A is 50%. Take note that this is multiplied to 100%. So, this is 50%. But in decimal, this is 0.5. What about the second dataset or dataset B? Equals standard deviation 2 divided by the mean, which is 56, times 100%. Okay. Okay, what is it equal to? 3 point, see, it's 3 point, did I multiply by 100? Okay, so it's 3.57%. So what can you say about the coefficients of variation, which has a higher value, dataset A? Okay, so dataset A has a greater CV than dataset B. Okay, so that's for problem number 1. What about problem number 2? Compute the coefficients of variation for the data in the table. Compute for the coefficient of variation for the data in the table where the birth weights are expressed in either grams or ounces. Okay, how many observations are there? We have here 5, 10, 15, and 20. Okay, 20 observations. So, what do we need to compute for the coefficient of variation? We need the standard deviation and the mean. Okay, so let's use Excel to find the mean and the standard deviation of this data set. So let's go back to our Excel file. 3,265, 3,265, 3,260, 3,245, 3,484, 4,146, I should say, 3,023, 3,323, 3,649, then 3,200, 30, 3031, then 2069, 2581, 2841, 3609, 2838, 3541, then 2759, 2759, 3248, 3314, 3101, and 2834. Okay, so before we can compute for the coefficient of variation, let's compute for the mean first, mean and the standard deviation. Okay, so mean, just the same. Use Excel function, type in equal sign, click on one cell, that cell where you would like the mean to appear, or you would like to display the average. equals average, and then simply highlight, okay, highlight all the scores in that data set. Okay, so the mean is 3166.9. Okay, how about the standard deviation? Let's use again the abbreviation SD for standard deviation. The standard deviation is equal to ST, and the standard deviation of the different types of standard deviations will appear in the functions. So since this is a sample, then we choose the second. Okay, standard deviation for a sample. Then highlight the scores and close it in a parenthesis. Okay, so the standard deviation is 44, okay, 445.33, and the mean is 3,166.9. So let's compute for the coefficient of variation. So again, coefficient of variation is simply S over X bar times 100%. So S over X bar, the mean, times 100%. Times 100%. Okay, so the coefficient of variation is when rounded up to the nearest tens is 14.1 or 14.06%. So let's check on our PowerPoint presentation. Okay, so correct. The coefficient of variation that we were able to compute is 14.1%. So that's how simple it is computing for the coefficient of variation. Okay, so the coefficient of variation is most useful in comparing the variability of several different samples. Like in our previous example, we have two data sets. They can compare their variability. Okay, take note that in the first example, the standard deviations are equal, each with different arithmetic means. This is because a higher variability is usually expected when the mean increases, and the CV is a measure that accounts for this variability. The coefficient of variation is also useful for comparing reproducibility of different variables. Okay, here is a data I obtained from CDC. Okay, data from a heart study. Okay, a large study of cardiovascular risk factors in children, which started in 1970s and continues up to present. And here is the table. Yan. Okay? So, the study looked into the following factors: height, weight, skin fold, okay, BP, cholesterol level, HDL cholesterol level. So, different means. The means are different. Okay, the number of observations also, and the standard deviation. And CVs range from 0.2. Okay, the coefficient of variations varies, or should I say ranges from 0.2 up to 10.4, which is the highest. Okay, so interpretation. So it says in 1978, replicate measurements were obtained. Now that's it. The table presents okay. CV ranges from 0.2% for height, 10.4 for HDL cholesterol level. The standard deviations are within. So we can compare even when the units are different. This is the meaning of this. The first statement here is most useful in comparing variability of different samples, even when the units are different. Okay? Even when the units are different. So looking at this table, we can compare the variability of the patients in terms of height, in terms of weight, in terms of HDL. by looking into the coefficient of variation. Now we move on to the next. Problem number 3. Okay, problem number 3. Activated protein resistance is a serum marker that has been associated with thrombosis, formation of blood clots, often leading to heart attacks among adults. A study assessed this risk factor among adolescents. To assess reproducibility of the assay, a split sample technique was used in which a blood sample was provided by 10 people. Each sample was split into 2 parts and assessed separately. Okay? I want you to compute for mean, standard deviation, and coefficient of sample A and sample B. Okay, I leave this as part of your assignment. So maybe skip problem B so we can move on to the next. Okay? So for problem number, it should be problem number 3. This is problem number 3. What are you going to do? Compute for the coefficient of variation by obtaining the mean and standard deviation. So we have 2 replicates, okay, A and B. So compare the means, the standard deviation, and the coefficient of variation for the two replicates for each subject. Now we move on to the next concept for this morning, which is coefficient of, or should I say, standard error of the sample mean. Okay, standard error of the sample mean. What is this standard error? Standard error of the sample mean. Is it the same as the standard deviation? Okay, remember that when we compute for standard deviation, we get the squared differences between the x value and x bar. Okay, squared differences divided by n and then subtract the square root. Okay, but what about standard error? What is standard error? The standard deviation is sometimes confused with this measure, standard error, but the two are not the same. Okay? These two measures are different. Your standard deviation describes variability in a set of data, while the standard error refers to variability that might be expected in the arithmetic means of repeated samples taken from the same population. Okay? The standard error assumes that the data you have is actually a sample from a larger population. And according to the assumption, the sample is just one of an infinite number of possible samples that could be taken from the source population. So the mean of your sample is just one of an infinite number of other sample means. Okay, the standard error quantifies the variation in the sample means. Okay, because you can change from sample to sample, and that would mean the mean also changes. Okay, the mean changes from sample to sample. So we have to quantify the variation in those different sample means, and that's where your standard error of the sample mean comes in. Okay, how is standard error of the sample mean computed? The standard error, okay, of the mean is computed by following these steps. Step number 1, first you need to know the standard deviation. Okay, calculate the standard deviation, and then step number 2, divide the standard deviation by the square root of the number of observations. Okay, what are some of the uses of the standard error? One use, primary and the most practical use of your standard error of the mean is when we want to establish or calculate confidence intervals around the arithmetic mean. So if it's a sample mean that means the population is very close to it. It may be less than the sample mean or more than or greater than the sample mean. But if we want to establish confidence intervals, okay, how confident are you? I'm 95% confident that the population mean is from this value to this value. But how do we establish that interval? Okay, that's the next part. But before we proceed to computing for the confidence interval, let's have first one problem illustration of computing for the standard error of the sample mean. Okay, problem number 4. I left problem number 3 as part of your assignment, okay? So this is now problem number 4. Find the standard error of the mean for the length of stay data in this table. Okay, table 2.10, I got this also from CDC. Table 2.10 is frequency distribution of length of hospital stay, sample data, okay? And the length of stay, first column. Then, okay, so find the standard error of the mean of the length of stay in the table. Given the standard deviation, so the standard deviation is already given. Okay, the standard deviation is given. All we have to do is to compute for the mean. Okay, considering this frequency. Okay, total is 30 because 1, 2, 3, 4, 6, 8, 12, 17, 21, 23, 26, 28, 30. Correct. 30 patients. Okay, 30 patients. So the solution is not provided. So may we have the solution here. What is this problem asking for? The standard error. So let me just copy the data. Anyway, there are only a few values. It won't take much time. So 0, you have 0, 0, 1 patient. Then we have 2, 1 patient. 3, how many? 1 patient. 4, 1 patient. 5, 2 patients. 6, 1 patient. 7, for 7 days, 1 patient. 8, 1 patient. 9, we have 3 patients. 10, 5 patients. 11, 1 patient. 12, 3 patients. 13, 1 patient. 14, 1 patient. 15, okay, 16. 15 none, 16 next. 16, 1 patient. 18, 2 patients. 18, 2. Sorry, 18, 2. 2 patients. And then 19, 1 patient. 22, 1 patient. 27, 1 patient. And 49, 49 days, 1 patient. So if you get the sum, the total frequency should be, okay, the sum of all these values, or auto sum na lang sana tayo. It's okay. The sum of all these values should be 30. Okay, so 30. So how do we compute for the mean? So mean equals oh, no, not yet. Okay, since this is group or presented in the frequency distribution, the frequencies are given. We first multiply the length of stay with the frequency, meaning multiply column C to column D. Okay? Drag this down so that the formula applies to the next or the succeeding columns. And then we get the sum or auto sum, up to you, sum of all these values divided by, okay, sum divided by 30. So, the mean equals, okay, 360 divided by 30. And what is it equal to? The mean is 12. Okay, so the mean is 12. And if we go back to the problem, the standard deviation is already given. The standard deviation is, let's go back. The problem says the standard deviation is 9.188. So we don't have to, okay, we don't have to compute for the standard deviation. It's already provided in the problem. Okay, what are we going to solve for? The standard error. So let's go back to our Excel sheet. Okay, so standard deviation SD as provided in the problem is 9.188. Okay, so SE, okay, SE, standard error is equal to, going back, okay, let's go back to our, okay, formula. The formula says standard error is equal to, okay, it's S over square root of N. S, the standard deviation, over, divided by square root. See, we also have square root here. Square root of, what's our N? Number of observations is 30. And then, okay, so the standard error of the sample mean is 1.68. Okay, so the standard error is 1.68. Once more, how did we get the mean? Multiply every individual, okay, x by the frequency, take the total, divided by n. That's the mean, which is 12. So, the average length of stay of the patients, 30 patients in the hospital is 12, mean. And how do we compute for SE? Standard error is, okay, let's go back. Standard deviation over the square root of n. Okay, standard deviation over the square root of n. Divide the standard deviation by the square root of the number of observations. So, in that case, our standard deviation is 9. We don't have to compute for or calculate the standard deviation, finish. Ito pala dapat ang ginawa natin, calculate the standard deviation, but it's already provided in the problem. Okay? Okay, the standard error of the mean is 1.68. Now we move on to the next. So let's say we want to know the average IQ of College of Allied Health Sciences students. So let's say we have a sample of 10 students who took an IQ test, and the following are the results. Okay, the marks or the scores, IQ scores of 10, a sample of 10 students from CAS, okay, are the following. Say, and the following are the results. Let's say 90, 100, 112, 122, 121, 108, 101, 126, 110, 98. Okay, 10 students. Okay, let's look for their mean. Mean equal to, so average Okay, so this is the mean. Let me insert one more row so we could label. Okay, so let's just highlight this. Okay, let this be the mean. How about the standard deviation? Okay, how about the standard deviation? Equals standard deviation. Okay, standard deviation of a sample. Okay, sample. Okay, so let's highlight this. Take note that the first highlighted value is the mean and the second in green is the standard deviation. Now the question is, how confident are we that this is really an estimate of the mean? We only took a sample of 10 students. Okay? This value, 110 is our best guess of the population mean. But because there are only 10 students in the sample, we are not very confident about this value. Okay, how many at the moment students are enrolled in the College of Allied Health Sciences? So if we take only 10 students and say that the population mean is around 110, how confident are you? Okay, so we're not very confident about this value. The mean may be below 110 or it may be above 110. Okay, so now let's extend the study by increasing n. Let's increase n. But prior to that, let's first compute for standard error so that we will see the difference between the different samples. Okay, so if there are only 10 in the sample, what will be the standard error? Okay, the standard error, once again, is equal to standard deviation over square root of n. Okay, so standard deviation over the square root. We also have square root function. See, equal to SQRT. If you type in SQRT, there you have SQRT for square root of 10. Okay, that's n, the number of observation. Okay, so this is the standard error. May I use another color, yellow this time for the standard error. Now let's extend. Dagdagan natin. What about if there are 15 students? So let's say 15 students now. So 90, I will just copy the first 10, control, and then paste. Then add other values like let's say 101, say 90, say 113. So how many values do we need? 1, 2, I added 101, 90, 113. Let's say another value, 100. And one more to make it 15 is, let's say, 98 again. So let's compute again for mean, average of these values. Okay, from 16 until B2. Okay, so the average is 106. Okay, the average is 106. Let me use so that it will be consistent. Red for not. Okay, mean is red. The mean is red. The standard deviation SD is in green. And that one in yellow is the error. Standard error of the mean. Okay, so let's continue. How about the standard deviation for the next set consisting of 15 samples, or should I say 15 observations or 15 students? So S standard deviation of a sample. Okay, highlight the values and close it in a parenthesis, and there it is. Okay, almost the same as the previous standard deviation. But let's look at the error. Okay, will it vary? So again, standard error is equal to standard variation or standard deviation, I should say, over square root, SQRT for square root, of this time, how many students? 15. Or how many observations? 15. Okay. So look at the standard error. What have you noticed? Compared to the previous, the standard error is now 2.88. Before, when there were only 10 students in the sample, it's 3.711. What more if we increase the number of samples? Okay, what if I increase the number of samples? Increasing n. So let's make it 20. And let's see what happens with the standard error as we increase the sample size. Okay? So what have we done so far? Increase the sample size from 10 to 15. What if I make it 20? Okay, let's make it 20 so that we can contrast it also to 15. Okay, let's add 5 more because this has 15 observations only. So we need 5 more. Let's say 112, 100, 90, same 101, and 100 again. Okay, so that's from, we ended with 98. So 1, 2, 3, 3, 4, 5. So we added 5 more, making our sample size 20. Our n is 20. Here, our n equals 10. Okay, here, n equals 15. Now we have n equal to 20. Let's look for the mean, average. Okay, so average, once again, highlight all the scores, highlight all the observations, and then, okay, so this is the average, 104.65. Okay, let me use to be consistent. Okay, now, what about the standard deviation? Standard deviation of the sample equals, highlight again, once again, all the scores for, okay, okay, so this is it, 10 point, the standard deviation is this, use, okay, and finally, the standard error equal to, the standard error equal to standard deviation over equals square root of 20. Okay? Because now we have 20. Yes, sorry, but nag-equal sign ako. You don't have to. Okay, so see, what happens as we increase? Okay? As we increase the sample size, this is now for n equal to 20. Okay, so when n is 10, the standard error of the mean is 3.71. When n is 15, the standard error of the mean is 2.89. When n is 20, the standard error of the mean is 20. So what can you say? Okay, increasing the sample size, what is the effect of increasing n? Increasing the sample size, okay, decreases the error, yes? Decreases the the higher the number of observations, the lesser the standard error. Therefore, the higher is your confidence. Okay? So the higher the confidence level is higher. So how confident are you that this is the mean? Okay? How confident are you that this is the mean IQ of students in class? All the more if we increase our n, the standard error will be lesser. Okay? So what is the effect of increasing the sample size? The higher the number of observations, the lesser the standard error. So, the more confident you are. Okay? Now, we have a measure of uncertainty around the mean. So, we are not certain if it's 104 from maybe it might be below 104, okay, or above 104. Exactly from which value? Below 104 by how many units? Above 104 by how many units? Okay, and that means we have to establish our interval. Okay, so that we can say I'm 95% confident that the population IQ or IQ of students in College of Allied Health Sciences is from this value to this value. But how do we establish that value? That's the next question. So, a direct application of your standard error, go back to our PowerPoint presentation. Yan. Practical use, although I mentioned this a while ago, is in calculating the confidence interval. Okay? So if this is the sample mean that you have computed, maybe the population mean could be somewhere here. Okay? Could be somewhere here or somewhere above. Okay? It could either be below this value, meaning to its left, or it could be above this value or to its right. Therefore, we have to establish an interval in which we are confident to say how many percent. No, we can even calculate 98%, 99%, 80%, or 95%. Are you 95% confident that the population mean lies within this range of values? Okay, how do we establish that? Okay, that's the next thing that we are to do. Confidence interval or confidence limits. It says here that, okay, sometimes epidemiologists conduct studies not only to measure characteristics in the subject studied, but also to make generalizations about the larger population. Okay, because we cannot also take all. Okay, so the reason why we have some sampling. Okay, review your sampling techniques. Yeah, now the process of inference is making generalizations about the larger population but from sample. Okay, from sample. This is the process called inference. Okay, for instance, your political pollsters, okay, during or prior to election, di ba? Use samples of maybe 1,000, 10,000 across the country to make inferences about who among the presidential candidates is likely to win during the election. And the inference includes some consideration about the precision of the measurement. The results of a political poll may be reported to have a margin of error. Okay? A margin of error, say plus or minus. Yun. Okay? Plus or minus 3 points. But in epidemiology, a common way to indicate a measurement's precision is by providing a confidence interval. Okay? From this value to this value. A narrow confidence interval indicates high precision. A wide confidence interval indicates low precision. Now, going back to the set of IQ scores in the previous example. So, we had IQ scores of 10 students, 15 students, and 20 students. We know that the true population could be a little bit lower or higher than the mean or the average that we have computed. So, the population mean lies so that the sample mean is going to be the middle. Okay? A few little steps to the left and to the right, and we come up with an interval where we might say that we are 95% confident that the true population mean exists inside, okay, or within that interval. So how shall we do that? So first we have to consider that the population mean must be quite close to x bar. Okay? There are two ways by which we can establish or compute the confidence interval. One is when we know the standard deviation of the population, then the confidence interval is simply confidence interval is simply x bar plus minus 1.96 times SE. Okay, times the standard error. Okay, so that's 1.96 plus minus, okay, but your SE, but the standard error is equal to S over the square root of n. For a sample, but for population, the standard error, if the population standard deviation is given, okay, sigma over the square root of n, or, okay, I'm using or. So we can simply calculate the 95%. Yeah, 95%, let me underscore 95% confidence interval for a mean total cholesterol level of 206, standard error of the mean of, okay, 3. So step number 1, step 1. Okay, we have to calculate the mean and its error. Okay, mean is given. What we are to calculate is only the standard error of the mean. Calculate the SE, standard error of the mean. Okay, and the standard error of the mean is equal to SE. Okay, standard error of the mean is equal to, or should I say, going back to the problem, it's already given, so we don't have to. Standard error of the mean is already provided, 3, and the cholesterol level is 206. So that we don't have to do. SE equal to 3, it's provided in the problem pala. It's given already. SE is equal to 3. Step number 2, suppose this is not given, then we have to compute for SE by the formula S over square root of n. Next, number 2, after calculating, or if SE is given, you just have to identify or jot it down and then multiply the standard error SE by 1.96. Okay, 1.96. Okay, get the product of the two. 1.96 times 3 is equal to 5.88. Now you might be asking me, where did this 1.96 come from? Where did this come from? Okay, from the Z table. If you could recall from, okay, from your previous math subjects about your Z table, okay, the areas under the normal distribution, let me show. Because you might be asking me where that 1.96, which is given in the formula, it's provided in the formula, but I just want to show you where that 1.96 came from. Okay, to show you where that 1.96 came from, okay. From the Z table. Okay, so this is the Z table. Let me make it bigger. Going back to the problem, what did it say? The problem requires that we establish a confidence interval of with 95% confidence level. Okay, where is 95%? What does it mean by that? In your normal curve, Let me draw your normal curve. The normal curve looks like this. Okay, so when we speak about 95%, so 95%, the total area under the normal curve is 100%. If it's a two-tailed test, if it's a one-tailed test, then the diagram would look like this. But if it's two-tailed, then that means we divide. Okay, your normal distribution would look like this. So the mu mean is at the center. The population mean must be at the center. So 95% confident means, let's say, the mean is, the population mean must be somewhere between this and these values. So this is our interval. So if the total area here is 95%, okay, so minus, then this must be 0.25, yes, percent. Oh, sorry, 2.5% rather. Okay, let me erase. 5%, the total of this is 95%. Once more. This is 95%. And so the two tails, which we have excluded, the two tails that we have excluded, if we get the sum, then that would be, okay, 2.5% each, yes? Because 1 minus 95% is 5%. So 5% divided by 2 is 2.5. Okay, so ito is 2.5% and 2.5%. Here to the left, area. Okay, from that which I marked in red to the left is 95% plus 2.5%, which is 90. The whole of this then, if I may use this now, inclusive of this, will be, the area will be 97.5%. If I subtract that from 1, that would be this area. Okay? 2.5%. So this is 2.5, then this, the shaded region is, okay, the shaded region, or from the red mark to the left, is 95%, 97.5% of the normal distribution. We look up in the table for that z value corresponding to, what is that z value corresponding to 97.5, but convert this into decimal. 97.5 is 0.975. So in your z table, in the z table, look for this value and check on the intersection. Okay, for 0.975, okay, this then corresponds to what z value or z score. The z-score, which corresponds to 0.975, is 1.96. That's where 1.96 came from in the formula. Okay, once more, how did we get 0.975? This is the area to the left, from our, wait 1 minute, from our, there, area to the left from here, okay, ito, this area is 0.975, erase, okay. 0.975, this area, because 5% plus 5%, or 5% divided by 2 rather, this in fact is 2.5, not 5%. This is 2.5 here, 2.5 here, make it, okay, 2.5 on both ends. So 2.5 plus 2.5 is 5%. So 95% is within that interval, okay? Or between this, okay, this two. But when we look up for z value from the table, it gives the z value to the left, the positive values of z value to the left. So from here then to the left, the total area is 97.5, because if this is 2.5, this is also 2.5, 2.5%. So 95% plus 2.5% is 97.5%, or when expressed into decimal, 0.975. So table lookup, tingnan lang yan sa table. So yan, 0.975. Yan, 0.975. Let's use this color. Okay. And, okay, so 0.975 corresponds to what z value? 1.96. 1.96. Diyan galing yung nasa formula. Mean of 206 and a standard error of the mean of 3. So, how shall we, okay, compute for the interval? Again, using the formula, x bar plus minus. So, to the left and to the right. Plus minus, what's z value? 1.96 because it's 95%. When can we use 1.96? Please take note of this, that we can use 1.96 only when the confidence level is 95%, because that's the most common. But for medical researches, it should be 99%. The accuracy should be up to 99%. So the confidence level should be 99%. But most of the researchers make use of 95% confidence level. So when can we use 1.95? Only when the confidence level is 95%. So plus, why 1.95? 1.96 I should say. We can use 1.96 only when the confidence level is 95% times the standard error. Okay? So our mean here is 206 plus minus, okay, 1.96 times the standard error, which is 3. Okay? Standard error of 3. And this gives, what will this be? 5.88. So this one is 5.88. So 206 plus minus 5.88. And this gives two values. The values are the lower limit will be 200.12, and the upper limit will be 211.88. So we round up to the nearest hundreds. So the 95% confidence interval is from 212 to 200, okay, 288. What does it mean? The best example or the best estimate of the true population mean is, okay, between 200 to 211.88. So the confidence interval indicates how precise the estimate is. So if the computed mean is, okay, 200 to 200.12 to 211.88, you are 95% confident that the true mean lies within that interval. Okay, so it also indicates how confident the researchers should be in drawing the conclusion or drawing inferences from the sample to the entire population. So that gives you your confidence level or confidence interval. Now, what about if this is 90%? or 99%. Again, you can look up from the table. If it is 95%, 99%, then 0.05, 0.05. Pag 99%, that would mean 0.9. Ay, hindi na. Nakat na ang table natin. Okay. But you can use anyway. You can stick to the formula x bar plus minus 1.96 times the standard error. Okay. Now, some of the uses of the confidence interval, properties and uses rather of the confidence intervals. The mean is not the only measure for which a confidence interval can or should be calculated. Confidence intervals are also calculated for proportions, for rates, for risk ratios, odd ratios, and other epidemiologic measures when the purpose is to draw inference from a sample survey or a study to a larger population. Okay? Most epidemiologic studies are not performed under the ideal conditions required by the theory behind a confidence interval. As a result, most epidemiologists take a common sense approach rather than a strict statistical approach to the interpretation of a confidence interval. Okay? Confidence interval for means, for proportions, for risk ratios, for odd ratios, and other measures are calculated using different formulas. So this is just one. The method that I presented this morning is only one. So there are a number of formulas. You can use t-value. You can use Excel, in fact. Regardless of the measure, the interpretation of a confidence interval is the same. The narrower the interval, the more precise is the estimate. And the range of values in the intervals is the range of the population values most consistent with data from the study. Okay? So this is all about confidence interval. Now, let's look into another example of a problem on establishing or computing for confidence interval. Let this be the last for this morning. And then the rest I will give as part of your assignment. Okay, so let's take a look at this time 90%. Okay, kasi sabi natin if confidence level is 95%, we use 1.96, that factor 1.96, okay? What if the confidence level is 95%? Okay? If the confidence level is 90%, we use, what shall we use? If the confidence level is 90%, then we shall use 1.645 for, from the table, once again, bakit 1.645? You might be asking again, why 1.645? So, draw your normal distribution. Let this